Okay, shall we make a start, right? Are you ready, guys? Are you ready? Yes. Last push. It's like, maternity ward. Push, last push. Then we get it done for today. Right. Just to carry on from where we left off before lunch. Well, my lunch, you obviously were busy with Helen's material. We were talking about this confidence interval, and we said we have now a way of calculating a confidence interval where we believe that the true population mean is located. And I've given you, after all this, how shall I say, statistical foreplay, I've given, sorry, I've given you this really simple equation where you can calculate this confidence interval. But unfortunately, there's a slight problem. It's always a problem, right? It seems sort of I'm a problem magnet. I attract problems constantly. I mean, just last week, problem, our electricity didn't work. Just went. You don't want to know what happened. Actually, I tell you anyway. We had to call an electrician out. The electrician found the problem. The cat pissed into the wall socket. It's constant problems. When you are with me, it's a constant problem. This time it wasn't me who did it, but it was the cat. But Anyway, here is the problem, and you can see it. It's plain obvious. The problem. Let's see if any one of you spots the problem.
Use the thing of the population.
It has something to do with that. You're absolutely right, Callum, because we don't know the sky. We don't know the standard deviation of the population in most cases. Sometimes we do. With the IQ test is set up that the population standard deviation is 15. That is how it was designed. So therefore, we can be fairly confident that this is indeed the case. But usually, we don't know this standard deviation of the population. That's why we have to estimate it. And we said we can estimate it with this S, with the standard deviation that we calculate where we do the n-1 trick. Yeah. So usually we would have our population mean that we estimate from the sample mean, that's this x bar, plus minus, and instead of the sigma, we write S over square root n. That's still the standard error, in this case, standard error of the mean. So that's good. But it turns out, because we do not know this population standard deviation, we cannot use the normal distribution. Bugger it. Yeah, normal distribution was so nice, was really cute, it was a nice bell-shaped thing. Well, we could do a lot. If we were inclined that way, we could have a lot of fun with it, with this normal distribution. But now we can't use it because it only applies, normal distribution only applies if we know this sigma, normal. Only if we have sigma, we can use the normal distribution, and as a consequence, we can use this factor of 1.96, or if you like 2, basically. But if we don't know this sigma, we have to use another number, not 1.96. We actually have to use another distribution, and this distribution looks similar to the normal distribution, but has a few quirks. This distribution is called the t-distribution. So whenever we know sigma, we can use the normal distribution. But if we don't know sigma, we have to use the t-distribution. What does the t-distribution look like? The t-distribution is a little bit of a pig, because there's not just one t-distribution. The t-distribution actually is a whole bunch of distributions which all look fairly similar, but they differ in one particular aspect. Just to let you see. Sorry?
There's just a lot of grass on there. As in like the bit above, well, don't worry.
Grass?
Grass.
Grass. Oh, don't worry about that. I will torture you with that later.
Okay.
So the t-distribution is a whole bunch of graphs. They all look pretty much the same, you know, from the shape here, a little bit like the bell curve. But the difference between these distributions, these t-distributions, is in something that is called df. What the hell is df? Let's put it here. So df. df stands for degree of freedom. And it doesn't mean that they can run around wild or something like that, that they are free to do whatever they want. Degree of freedom is very closely linked to the sample size. And I give you an example. Let's say we have an equation, a plus b plus c equals 15. Yeah? Can you tell me what a is from this equation? No. Why not? Surely it's not that difficult.
You don't know what B and C are.
Aha.
A could be 10, B could be 2 and 3.
Aha. Okay. Okay. So A, let's say A is 10. Yeah? What is B and C? Can you tell me what B is? No. Okay. Let's say B is 2. Can you tell me what C is? 3. Ah, now you can do it, right? Aha. So this equation that I've written down has actually 2 degrees of freedom. I can choose 2 of the variables, A and B, or I could choose A and C, or I could use B and C. I can choose them. I'm free to choose them. And the third variable will automatically result from that. Yeah? So this one here has 2 degrees of freedom. Bless you. What would you say, from your intuition, what is the equation for the degrees of freedom? Number of variables, number of observations, minus 1. So in this case, df equals n minus 1. So we've got the degrees of freedom, basically what we can change, and the last one will basically follow automatically. And that is exactly what the t-distribution actually does. It is a bunch of distributions. And if you look at, for example, this one here, this pink one, that's the first one. Where is it? That's this one here. It looks like a little bit like the normal distribution, but it's a little bit lower down, and it has heavier tails. These bits towards here and bits towards here are heavier, are bigger than in the normal distribution. And if you go up with the degrees of freedom, so if your sample size, for example, is getting bigger and bigger, because that is exactly what these degrees of freedom are, your t-distribution becomes more and more similar to the normal distribution. So here, for example, the green one has 20 degrees of freedom. So we have a sample size of 21. And it's almost indistinguishable from the normal distribution. If you have a sample size of 30, 40, 50, 2,000, you can't tell the difference between the t-distribution and the normal distribution. That's why, for example, people always say you should have a sample size of at least 30. If you've got 30 observations or more, then it is pretty safe to work with the normal distribution and to work with this 1.96. But if you want to do smaller sample sizes, people usually say, no, you have to do the t-distribution. I can give you an example. When we have this t-distribution and we have say 3 observations, just 3 observations. How many degrees of freedom?
2.
2. So 3 observations. Would be degrees of freedom equals 2. And this factor of 1.96 is no longer 1.96 because that would be for the normal distribution. This factor here would be what is called a critical t-value. And the critical t-value in this case would be 4.3. So it goes up. What is the consequence with this factor getting bigger? The consequence would be that our confidence interval would also get bigger. Yeah? It does make a difference whether we multiply with 2 or with factor 4.3. Yeah? You agree? Makes a huge difference. Factor 2. So our confidence interval here might have been like that. Now our confidence interval is like that, because we have to multiply it by factor 4.3, not 1.96. So we are less certain. And in a way, if you think about it, the intuition is it makes sense because we have far less information. We only have 3 samples, and we don't know actually what the true variability in the population is. So therefore, we need to be far more conservative and span out this confidence interval so that we can say we are fairly confident that the true mean is somewhere in this CI, in this confidence interval. And because we use this sort of our confidence level of, say, 95%, we call this a 95% confidence interval. Yeah? And very often 95% confidence intervals are usually in square brackets with lower bound and upper bound included. Now, this t-distribution is applicable if we have small sample size, usually people say less than 30, and if we don't know sigma. We don't know the population standard deviation. In fact, I would actually be inclined to say, forget the first point, the major criterion for using the t-distribution is if we don't know sigma. Let's not worry about the sample size, because if we've got a large sample size and we use the t-distribution, it still looks like a normal distribution, so that's fine. We don't make any boo-boo there. But if we don't know sigma, we always have to use the t-distribution. Yeah? There's also another requirement. T-distribution only works for continuous data a t-distribution for discrete data doesn't make any sense. And that's the kicker. The sample must come from a normal distributed population.
What does that mean?
That's a very good point, and I'm going to explain that immediately. We take the sample and we make the assumption that whatever we look at shows this normal distribution in the population. So when we take the entire population, we will find this typical bell-shaped curve. Yeah? Normal distributed. And with these characteristics, 68% within the first standard deviation, 95% within 2 standard deviations, 99.7 within 3. Yeah? And it's very common. But it doesn't have always to be the case that this is indeed, that this is the population. Unfortunately, we don't know for sure what the population looks like. We can just simply, we can only use the sample and think, yeah, it looks all right. So it's probably from a normal distributed population. So we can work with that. But there are a number of other possibilities. These are these graphs. Don't panic. Don't start to hyperventilate. A population can take on a number of different shapes. You see sometimes even the population data can't take on every single number. So for the normal distribution, yes, it can. For a t-distribution, it can. For other populations, it can't. So for example, throwing a dice. The population is basically all the sort of the dots that you can see. And it can only be 1, 2, 3, 4, 5, and 6. Nothing in between, but that would be the population. Could you use the normal distribution for that? No, absolutely not, because it's discrete and it's not normal distributed. Yeah? So you need to know what are the data. If the data are discrete, hands off a normal distribution. It's a no-no. If the data are continuous, you might be lucky that it is a normal distribution, so carry on with a normal or a t-distribution. But if they are not normal distributed, it could get to weird results. And there are tests how you can check that the sample that you have taken come from a normal distributed population. So for example, if you have a sample, and when you look at the sample looks a little bit like that. Okay, I take that. Looks like that. Is that normal distributed? It doesn't look perfectly like a normal distributed sample. Mind you, the sample doesn't have to be normal distributed. It is the population from which it comes that needs to be normal distributed. So, what do we do with that? Or maybe we have something like that. Does that look normal distributed? No, it's a bit skewed, isn't it? Now, there are tricks that you can use. If your sample looks like that, if it doesn't look total whack job and be totally all over the place, if you say, if I squint a little bit and just close one eye, yeah, it could almost be. There's a nice trick that you can do. You can do what is called transformation of the data. So for example, if you've got something like this here, where it is skewed, what you can do, and that's a sort of a really dirty trick. You need to be a bit careful with it, but sometimes it works quite nicely. Instead of using your sample data, what you do is you take the logarithm of the sample data. Of all the data, you calculate the logarithm. And all of a sudden, your weird skewed distribution will show a nice normal appearance. So that is how you can, when you see that the sample looks a little bit weird, try to take all values, logarithm, or you can do other transformations. Logarithm is the most common one. And all of a sudden you get a nice normal distributed sample. Don't forget, what you get for the sample mean here is not the initial mean that we had, it will be the logarithm of the sample, of the population mean, when you do a log transformation. So that is how you can convert samples that are apparently not really normal distributed, or from a normal distribution, but they look a little bit funny, right? Do a log transformation and it looks much better. But don't forget that everything that you get is logarithm in this case. Right. So how do we find this critical t factor? Here's the deal. Life is difficult enough, especially with cats peeing in the wall socket and things like that. And, you know, to top it, I said to my wife, if that cat shows any further transgression, it's going to be kitten tikka masala. Guess what? This cat, half an hour later, brought in a rat. Yes. And do you know what's worse than a rat in the house?
Half a rat.
Half a rat, exactly, with the innards hanging out. And yes, thank you. Have I got you awake again? Just with this image, you know, need brain bleach. Well, we needed bleach as well. Just to make life a little bit easier for ourselves. Nobody in their right mind is going to calculate confidence intervals by hand. You will be pleased to hear. Yes, you'll be pleased to hear. So how do we do that? Of course, we use software. You can do it in Excel, but my advice, especially for your assessments, will be to use an online calculator. I'll give you the link to that in a minute. I just want to show you what you can do with that. So for example, here is a data set. I don't know what the data are. I think they were the diameter of a tumor in micrometer or something like that. So we measure some cancer patients and we get these tumors all at the same stage. And we want to know what is the population mean. We can't measure every single cancer patient. But we can estimate what the mean is if you've got this cancer in this at this stage. We can measure that, and we can figure out what is the confidence interval for it. And here I would strongly advise you to bookmark this calculator. It's a fantastic online calculator. Make it a little bit bigger. Does it work? Yeah? Okay, so if you click on that link and bookmark it, you might need it. It's really good. What you should come up with is something that looks like that. Is that right?
Yeah.
Yeah. Now, this online calculator allows you to do several calculations for several data types. And that is why it is really good, why I like it. What we are looking in this particular example is actually not on this tab. It is on this two-sample t-test tab. So if you click on that, what you will find here on the right-hand side are actually our data. How did the calculator know what data I wanted to put in? Actually, the calculator didn't know that. I just copied the data previously and showed you the data first. But that is sort of the example so that people know what they have to put in. So here, these are our data. It's the sample raw data. Here, and we are just looking at the top graph, it shows you what the normal distribution of the data in the population would look like. So that's the normal distribution. It assumes that the data come from this normal distribution. It will calculate straight away the mean of the data, 58.175. It will calculate the margin of error for 95% confidence interval, plus minus 23.42. And it will also show you even the lower bound and the upper bound. So it does fulfill all your dreams, all your wildest dreams that you might have in statistics. It gives you basically all the information. All you really need to do is put in the data. You can even copy them from Excel if you want. And it will do all the calculations. If you want to do the calculations by hand, be my guest. You have 8 observations, so it would be a t-distribution with 8 minus 1 degrees of freedom. You can, in theory, calculate the critical t-value if you really want to. But to be perfectly honest, my life is too short to do that. So I use usually this calculator, and it will give me the upper and the lower bound. And I can be fairly confident that the true population mean is somewhere between 34.752 and 81.598 micrometer in this case. Happy with that? So please, please, please utilize this online calculator when it comes to your assessments. I didn't say that really, but of course you can do it by hand. Here I showed you again. This is what I showed you in here. So we can figure out a confidence interval for any data type, for any data, and as long as they are continuous and we believe they come from a normal distributed population. And for our purposes, we just simply assume that everything is from a normal distributed population. If you've got the suspicion it's not, you do the log transformation. But I'm not a cruel person. My wife will probably say differently, but I will not subject you to a distribution that is not normal. It's just, no, it's not worth it. What can we do with these confidence intervals? Actually, we said we can estimate where the true population mean is, but we can do also something else. We can actually compare confidence intervals, or we can also put confidence intervals in our report. And that is something that you really must do when you write up your results. When you do some statistical analysis, you always need to put in your sample size. You always need to put in your standard deviation, probably the standard deviation that estimates the population standard deviation. And it's good practice to put in the 95% confidence interval. And that is what you get with that. So what you can do is you can do a bar plot. We said yesterday, some people put a standard deviation in, like that. But more useful, actually, than this standard deviation would be an error plot that shows the confidence interval. So you obviously need to put in the legend what this error bar is. So error bar equals 95% confidence interval. Because that allows us directly to compare two or more samples with each other. And here comes the trick. This is, don't tell anyone that I said that, okay? But this is a cool trick. This is absolutely amazing. Let's say we have sample 1 and we have this confidence interval. Yeah? So we assume that the true population mean is somewhere in this black line. Now we take another sample and we calculate the next confidence interval. And we find this confidence interval. Do these two confidence intervals overlap? No. What does this actually tell us, the way I've drawn it? Think about it. What does it tell us? We believe that the true population mean for the population from which we have sample 1 is somewhere in between here. Yeah? For sample 2, we believe that the true population mean from which we have taken sample 2 is somewhere here. These two confidence intervals don't overlap. So one says the true population mean is here. The other one says the true population mean is here. What's your conclusion? Sorry? Sample is not representative. That could actually be the case, yes, but we assume that the samples are representative. The obvious answer is one of them is lying. Yeah. But we assume we have done everything right, so they are not lying. What would be the other conclusion? There are outliers in the sample. We have sorted out the outliers. What else? The confidence interval also already has taken care of small sample sizes because of the t-distribution. Shall I? Yeah.
Is there just a bigger confidence interval for the actual population?
No. It's the simplest thing. It means, it could mean, and usually it does mean, that the two samples do not come from the same population. Yeah? Sample 1 comes from population 1. Sample 2 comes from population 2. But the two populations don't have any overlap. So they are not actually coming from the same population. They come from two different populations. Does that make sense? Okay, sample 1 looks like that. Sample 2 looks like that. What does that mean? Confidence intervals are totally sort of, one is included in the other one. What could that mean? Let's play detective. What could that mean? Well, think about the populations. That's sample 1. And that is population 2. It could be the same population. We would actually expect something like that if it was from the same population. But it could also be two populations of which we don't see any difference. So we can't tell whether there are two populations or whether it's just one population. Yeah? So we can't tell whether there is a difference between the two populations. In the first case, we know pretty sure that there is a difference in the populations. They come from different populations. And the second part, we can't tell whether they come from different populations or whether they come from the same population. It's not possible. We can't tell the difference. What do we do now? Sample 1 and sample 2. Do they come from different populations? Yes or yes?
Yes.
Yes. What's your name?
Hitash.
Hitash. Hitash says yes. You're wrong. So, conclusion, They don't come from the same population. Tosh,
Also wrong.
you're wrong,
Yeah.
I'm very good at this, aren't you?
right? No, actually, you're right. In both cases, you're right. Actually, no, you're not.
Okay.
Sorry, I'm messing around. We don't know. We have absolutely no way of knowing from the confidence intervals if the two samples come from two different populations or whether they indicate the same population. At that point, we have no way of knowing. Yeah. But that is now getting quite interesting because imagine we have two data sets. So here we have two data sets. These are our tumors. And in one case, without drug, without a treatment, and in the other case, with treatment. Yeah? And we would want to know whether there is a difference in whether the drug makes a difference, actually. Does the drug work or not? What's your gut feeling? Does it work?
Yeah.
Yeah?
Yeah.
You say that so confidently. What makes you say that they are different?
With the drug, the tumour size is smaller, but we don't know that it changed that many times. So our initial guess, yeah.
Initial guess. Okay. I've done a little bit of calculations here. And these calculations you can easily do. So we find that the average tumor size in the without drug is 58.2. That's the standard deviation, sample size, and that is the standard error. Whereas with drug, it is 33.7. So compare 58 to, say, 34. So you would say they are different, right? Now, of course, we must not just simply compare the sample means, because we know that the sample means could be different from each other. Why? What is the key word here? Why are they different from each other? Think about herpes. Because of the sampling error. This difference could just be due to selecting from the same population, but just by chance, and it's a small number, just by chance we select some that are smaller. Or it could be that there is indeed something in it, that there is a true difference, that they come from truly different two populations. It is basically similar to this case here. It could be that we have this one. It could be that we have this one here. And we don't know. We have absolutely no way of knowing which is which. So what we really need to do is we need to come up with, and I know you absolutely love that, the clinical trials people What do they love most? I'm looking at money. Yeah, okay, good. That's. What do they love most? Protocols. They love protocols, right? Everything has to have a protocol. So we need to come up with a protocol that allows us to test whether the two samples come from the same population or whether the two samples come from two different populations. Make sense? So we need to develop a protocol how we actually do this. How we take our sample that we've taken from a patient, got your tumor. Sorry, I hope you don't. Hope you don't have any. We take your tumor, measure it, and then you are untreated, you are treated. Take the tumor, measure it. Is there a difference between the tumors? Do the tumors come from different samples? Oh, from different populations? Or do they come from the same population? So we need to develop a protocol, how we can test that. So, protocol. And we need to sort of develop step by step how we test for that. Because at the end of the day, this will help us to decide whether the sample without drug and with drug come from the same population. Then we can say, no, it doesn't make any difference whether I give the drug or not. So in other words, the drug doesn't work. Or if I say, well, it's two different populations, minus drug is different to plus drug. So actually, the drug might have an effect. And that is what you guys are doing all the time, basically, in clinical trials. Test whether two samples are taken from the same or from two different populations. So let's develop the protocol after a 7-minute break. Shall we? Break time, if you are not awake yet. Bedtime,
Because you did vectors, not a specific vector.
Yeah, no, I did gene therapy and then about vectors. So I just did, but they got all that around vectors. I did non-viral vectors, viral vectors, and then oncology treatment using vectors. So how important and how to improve using vectors, and gene therapy. I don't remember them exactly, but just get rid of them. And also like laptop pain management. one I did like a trial for payment and we had talked about affecting on the red, and then I did like this adverse effects of payment drugs, and then I did one on like some other topic.
Whereas I would like being, it should be added, not promoted.
And I did the mode of action in the introduction. And when I had the folders, I kind of suggested that as well.
Yeah, so I'll just do an area, not a specific
Oh,
direction.
yeah, my first one was on overdose.
Oh, somebody left.
Oh, no.
Oh, that's yours.
Oh, yeah, I'll take it.
No. I'm not. Don't need it.
I'll just get my own one.
You just don't leave it here because they are gold dust.
So I'll just,
I submitted it.
wait, did you put some specific journal, was it?
Yeah.
Oh, you did? Oh, what did you get? Oh, oh, it's okay, it's okay.
Yeah, I just say, and I did like, because even that, like, we did an aerial therapy, it's like, I did like,
Yeah.
yeah, it's fine. I think more like. But then she gave me one, and then I was like, oh.
Yeah, no, I just like panicking, so it was obviously send an area of therapy rather than.
And then she does say, she was like, oh, like, in the,
Yeah,
in the sign, I got my second one recently, I got the first one like, and then I did. You don't have any monitors on?
I've got one.
I was trying not to be gone. Well, where's the ticket? Oh, I spent so long, the IT guy.
Oh, true.
Yeah, I think everyone has that, because it's the protocol name. Yeah.
Yeah,
Yeah.
study protocol. I started to, I can't do things like that, so like my behavior is.
Yes.
And that's just a
Like, I'm really trying to be
national
in the moment, you know, it's not like people.
Yes, I was just
I mean, reading it is the long part. Did you read
It's
the whole thing?
choosing what you're gonna add. What'd you say?
I said, why don't you register me to your?
Oh. Okay, so this was mine. It was. Yeah, I would on platforms and then enhancing positioning. Yeah. It was gene therapy.
How long is yours anyway?
It was. I think, yeah, I stayed in like. 878, but she didn't say anything about it. I think mine was 840, which is so. It was like about gene therapy, so biometric platforms, gene therapy, emerging non-power.
How many questions did you have? Just that one? Or was that?
No, I had that one and then. Here, I was unlucky. I had another one at the table, but.
It's about to die.
Yeah.
Try it.
Oh,
Yeah, it's working.
yeah, this is the other table. Okay. It's hard because there aren't any charges in there.
I was
No, like all the charges are not next to like the table.
No, it should be like now this.
Are you still happy for, non-statistics stuff, sort of data concepts?
Yeah, the concepts are okay. I think it's just sort of figuring out how I'll be using it in my we'll be using 36 in my work project.
Okay. So what's your project?
I have not. I'm still in the process of being
Okay.
thought about. Yeah.
Okay.
Because obviously I have to think about how to get the data in a more simplistic way.
Mhm.
So that it's not too complicated for me to process it.
Mhm.
Or I'm also thinking about how I change questionnaires into numerical data that can be then
Mhm.
sort of like processed and that. I don't have the questionnaires just yet, but it's just
Questionnaire
yeah.
design. On my website, there is something about how you make life easier designing questionnaires for.
Oh, okay.
So have a look at That's in the introduction, questionnaire design.
Is it this website?
Wait a moment, I show you.
Okay.
Scan it.
Okay, that's those the
Is that,
ones.
yeah? Under introduction,
Under
what do we want to know? How do we get the data? Have a look at that.
scripted. Nice introduction. So studies and all data.
Data. Oh, no, sorry, it's self-study. How do we get the data? Overview of study. This I thought I did. Oh no, where's it gone, Mama?
Okay.
What do we want?
How do you get the data? There we go. There we go.
Single. What do we want to know?
Okay, good practice in questionnaire design.
Yes, that's the one.
Okay.
You should be able to just click on it. Should be a slideshow.
But I mean, you can turn the noise cancelling
Does
off.
it?
You can also
Yeah.
make it,
Yeah, it is.
it detects other people's voices. So it turns the noise cancelling off so you can hear them.
Wow. No, that is good.
Yeah. It's pretty good.
When did you get that?
Very useful.
Does it make sense?
Yeah, it does.
That's great. I mean, I've got it shaped there.
All the questions numbered, so not A, B, C, but it's 1, 2, 3, 4, 5. And then, yeah, for stone theoretic, it's just 5, 4, 3, and it's easier then to change that from an A to B. And also,
What sometimes might be very helpful, some people do what's called Likert scales. So 1, 2, 3, 4, 5. They are total pig to analyze. Yeah, they are difficult to analyze. Sometimes, if you've got the option of an online question, make the participant use a slider from, say, 1 to 100. Because then you get a far more fine-grained number, which is not brutally discrete, 1 or 2 or 3, but it has sort of, it's almost continuous, which you then can use with t-tests. Does that make sense?
but also, one of the questions, I leave it blank, I say, how can we sort of help you expecting text?
Oh, text.
Yeah, and they can text, how to analyze.
Text analysis.
Yeah.
Very good question. Actually, there is now AI that allow you to do what is called a semantic analysis. Yeah. So you put in a text in and say, is that a positive result or is that a negative result? Yeah. Or what does the customer, the patient, actually want to say with that? And the AI will sort of try to guess. You obviously have to check, but you then can ask, what is it? On a scale of 1 to 10, how would you rate what this person just said in terms of, let's say, usability of the medical device or something like that. Yeah, something like that. So AI can help you.
Because I can imagine if I have 100 responses
Yeah.
of wording, not everybody is going to say anything.
Well, again, I think the statistics package that I said has a package that does some sort of semantic analysis. But I don't know what the name is. Okay, are we back, everybody? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Fantastic, we are back. Lovely, thank you. So, last push. We do a protocol. We do protocols. Protocols are wonderful because they set the rules, how we deal with things. And what we are actually going to do is something that is called hypothesis testing. Yes, I know. I feel your pain. So, PTSD?
A little bit.
A little bit. From school?
Yeah, A-level.
A-level. You did hypothesis testing?
Yeah, we did it in psychology.
And it was fun?
It was definitely something I remember vividly.
Because it was so horrible.
Yeah.
Okay, let's just take the sting out of it, okay? I shouldn't have told you that it is hypothesis testing. I should have just told you that as we are developing a simple protocol. Okay, we start off with something very basic. The basic thing is, step 1, we start off with what is called a null hypothesis. And you all have formulated a null hypothesis already today. Did you? Yes, you did. You probably didn't know that you formulated a null hypothesis, but you did. When we were discussing Hope's case, what was our first sort of point of call?
Innocent.
She is innocent, not guilty. Yeah? That is actually a null hypothesis. And the alternative hypothesis, you also formulated that she is guilty. That was done without seeing any evidence. And the null hypothesis in statistics works exactly the same. Now, null hypothesis testing is incredibly boring stuff. I have to warn you. Scientific hypothesis testing is exciting. Hey, my hypothesis is that the drug will work and, it will cure you of cancer. That's my scientific hypothesis. A null hypothesis is, it's actually always the same wording. The null hypothesis is actually abbreviated with H0 or HO or something like that. And it's always the same thing that it says. It says there is no difference between the two population means from which the samples have been taken. It's always the same wording. Do not mess with the wording. It's always the same. It's just a sort of a statement. There is no difference between the two population means. Any difference that we observe when we look at the samples is just simply due to sampling error. We can explain any differences by sampling error only. That is the null hypothesis. End of discussion. Job done. Right? That is the equivalent of not guilty. And why is it called null hypothesis? For a very simple reason. We can actually write this mathematically. We can write that the two population means mu1 equals mu2, or in a different form, mu1 minus mu2 equals 0, null. That is why it's called null hypothesis. Simple, no fuss. Is it bad?
Not particularly.
Fantastic. So that is our equivalent of not guilty. Any differences that we see in the samples is just simply due to sampling error. In other words, null hypothesis means, bless you, the samples come from the same population or from two populations which we cannot tell the difference between. Now, for the alternative hypothesis, we do exactly the negation of the null hypothesis. We just simply say there is a difference between the two population means from which the samples have been taken. And it's population means, it's not the sample means. We don't deal with the sample means because, because of the sampling error. Alternative hypothesis, there is a difference between the two sample means, and we can write this in this form as sample mean 1 is different from sample mean 2. Or we can also write it as mu1 minus mu2 is not equal to 0. Yeah? Now, in this case, we have two options. It could mean mu1 is smaller than mu2, or it could mean mu1 is larger than mu2. Either way, this would hold true. Yeah, this would be okay. So we've got two options, and therefore, what we apply is called a two-tailed test. Two-tailed test, because we've got two options. And this decision whether it is a two-tailed test comes from the way we phrase the alternative hypothesis. Of course, we could say we are not so much interested in whether there's no difference between them or whether there is, just a difference. We want to know whether it's just mu1 is smaller than mu2. We are only interested in this one. So we would only test for this one. Could be. We only want to know whether the drug shrinks the tumor. We are not interested in seeing whether the drug increases the tumor. Yeah? Then we have only one option. If we go for one of these, just one, then it would be a one-tailed test. So by formulating the null hypothesis, we sort of set ourselves up. Do we want to know whether there is a difference? Or do we want to be more specific? The general rule is always, until somebody really specifically asks you, always go for a two-tailed test to make life so much easier for yourself. Always go for a two-tailed test. So this would be basically this one here. So that is our initial step, the setup test, the setup step in our protocol. We formulate the null hypothesis and we formulate the alternative hypothesis. And as I said, it is such boring stuff because it's always the same wording. It's, don't mess with the wording. Okay, you could say, maybe you're not interested in the mean. Maybe you say, do they have both the same variance? Then you do that and replace mean with variance. But otherwise, do not touch the wording. That's the null hypothesis and the alternative hypothesis. End of discussion. That was step 1. Step 2, as you can see, we set the significance level. We set the level that we feel comfortable that we can make a mistake, a type 1 error, as we discussed today. Type 1 error, remember, we say she is guilty, although she is not. Usually, in most cases, you would probably set this alpha to 0.05 or 5%. That's a common value. Why 5%? I have absolutely no idea. In hardcore science and sometimes probably in clinical trials, you can set it to lower. You don't want to convict poor hope easily because it could have dramatic effects on her future career, right? So you could set it to 1%. You could set it to 3.5%, whatever you want. But you have to state it. And the usual thing is 5%. The third step is you need to formulate some decision rules. So if the evidence is really damning, then we will convict her. If the evidence is la-la, then we'll convict her anyway, because it's just for good fun. Send somebody down. Of course, we don't do that. So we need to make a decision and find something how we can, measure that. So, and I come back to these decision rules in a let's do them. We say for these decision rules, let's go here. Decision rules. We try to figure out the probability that we observe evidence for evidence, and everything hopefully becomes clear in a moment. So we collect the data, we check her handbag, we do fingerprints on the chocolate box that is now empty and things like that, yeah? all these things. So we collect the evidence and we say, what is the probability that we detect this evidence, or even more damaging, given that the null hypothesis is true? We basically ask, what is the probability to see this evidence if we assume that she is innocent? We ask, what is the probability to observe data like we have if we assume that there's no difference between the two populations? Mathematically, this would be P, that's the probability of data, that we observe the data, given that H naught is true. And this horizontal, this vertical line means given. We always assume that the null hypothesis is true. We never assume that the null hypothesis is not true. So we always assume that you are not guilty. And now we look, what is the probability for all the evidence that we have? And only if this probability is below a threshold, that we set, and that is the significance level alpha, we will say she is, the probability that we see this evidence with her being guilty is so small, we don't believe in her being guilty anymore. Now, this probability actually has a name. What is this probability called? Probability of observing data like that, given that the null hypothesis is true. This is what's called the p-value. And the probability can only be a number, so probability can only be a number between 0 and 1. Probability of 0 means it doesn't happen. The probability that I am going to train as a car mechanic is absolute 0, because I have no idea what I'm doing. I'm not interested in it. And as soon as I do DIY, my wife puts the ambulance on speed dial. A probability of 1 means the event is 100% sure. You cannot get better than 100%. So if somebody says, I'm 120% sure that you are an idiot, then I go up to them, I smack them in the face and say, you can't be 120% sure. You can't have a probability more than 100%. End of discussion, right? And if you call me an idiot, yeah, you might be right. Okay, so probability can only be between 0 and 1. Our decision rule will be, we say, if the p-value, and we will need to discuss how we calculate the p-value, if the p-value is smaller than alpha, our significance level, our type 1 error, we will reject the null hypothesis. So the evidence is there. We want to have sort of 5% chance that we make the wrong decision in convicting here. But the evidence is there, is really damaging. So we reject the null hypothesis and say, terribly sorry, you will be convicted. Yeah, we reject the null hypothesis. The null hypothesis was not guilty. Yeah, makes sense? If p-value is larger than alpha, then it means we don't have enough evidence to reject the null hypothesis. We can't say we accept the null hypothesis. That's not possible. We can't prove our hypothesis. We can only fail to reject. The null hypothesis. Fail to reject is almost as good as proof. It's a little bit like, some people say it's in the semantics, but I think it's a little bit more. It's a little bit like instead of saying, I love you, I can't do that, obviously. But the next best thing is that I can say is, I don't hate you. Right? Can you live with that?
Yes.
Yes, good. Okay, good. I think my wife can do as well in this case. So we reject the null hypothesis if p-value is low. We fail to reject the null hypothesis if the probability is higher than alpha. How can you remember that? Do we have somebody from Australia here? No Australians? Good. I'm very glad. Because you need to say that with an Australian accent. And I'm not very good at accents, so I probably get it totally wrong. If p is low, h0 must go. We reject the null hypothesis. If p is low, it means lower than our type 1 error. On the other hand, if p is high, h0 can stay. Right? So if the p-value is higher than our significance level, we fail to reject the null hypothesis. If we reject the null hypothesis, we say the story about there is no difference between the two populations is not true. So therefore, we go with the alternative hypothesis. So in other words, if we reject the null hypothesis, we say the alternative hypothesis must be correct. If we fail to reject the null hypothesis, we say we don't have enough evidence to reject the null hypothesis, so therefore we probably go along with the null hypothesis. But we don't have enough evidence. It could still be two different populations or two populations, but we can't see enough evidence, enough difference between them. Yeah? So far, we have not done any calculations, right? We just set up the null and alternative hypothesis, we set up the significance level, and we set up the rules. And the rules are always the same. So how do we get this p-value? How do we get the probability of observing the data? So we need to find the p-value, the probability, by calculating a test score. So we do have some calculations. Bugger it. Actually, nah. Calculate test score. And depending on whatever test we are going to do, the test scores are differently calculated. But it's always the same principle. We calculate a test score. Now, what we are going to do in this case today is we calculate the test score how it was originally calculated by the inventor of this test. What we do is we calculate a t-score. You probably remember that, Callum? T-score?
Yeah.
Yep. Don't worry. Don't worry. Yep. And originally, this t-score was calculated as we take the two sample means and we just simply divide them by the standard errors of sample 1 and sample 2 squared. That would give us a test score. Maybe I should tell you a little bit about the inventor of this test. Because it is a local history. The guy who invented this test, one William Gossett, was actually born in Canterbury, 18-something. He then went off to, can't remember, was it Cambridge or Oxford, one of those prestigious universities, and did a degree in maths. And after his, I think, PhD, he got the absolute dream job. Does anyone know what this dream job was? He got a job at the Guinness Brewery in Dublin because they wanted somebody who could work in the most boring field in quality assurance. And so what they did was they had these big barrels of the black stuff, Guinness, and they needed to make sure that the quality was always the same, more or less, yeah? So before they hired Gossett, it was a sort of an empirical method to test whether the quality of the Guinness is the same. So on a Friday afternoon, usually the workers came along and tried the different barrels and said whether the taste was the same and things like that. You can imagine after 5 or 6 pints of Guinness, the productivity of the workforce miraculously dropped. They were all totally pissed at that point then. And the brewery said, we can't do that anymore. So we get a mathematician in who comes up with an idea how we can compare the different batches with each other. And luckily they found Gossett, who had the skills to devise a test and come up with basically this equation here. Where is it? With this t-score equation. And they tried it, and it worked beautifully. They managed to compare two batches, and you can only compare two things with each other. Compare two batches and say, yes, they are potentially pretty similar. There's no major difference between them, or yes, there is a difference between them, which is not just simply due to minor sampling errors. It's just there is a fundamental difference in it. Now, Gossett wanted to publish his work, and I don't know what your company's sort of policies are. Can you publish any work? No.
I don't think we can.
You can't, probably not. Well, the Guinness Brewery was a little bit more lenient. They said, yes, you can publish it under certain conditions. A, you must not mention the name Guinness because it's commercially confidential, what we are doing, because it's much better than our competitors do, where the labor force is still, totally pissed by Monday. And you must not, because people know that you are working for Guinness, you must not mention your name. You cannot do that under your name. And Gossett said, so what can I do then? And he had this glorious idea. He published this test under a pen name, under a pseudonym. And he said, well, actually, I am still considering myself a student. So my name is now Student. And then he had this idea. He had a notebook, and apparently there was test notebook on it. And he said, why don't I call this just simply a student t-test? It was anything but tea that he tested. He actually tested Guinness, but that is what the name of this test is. It's a student t-test.
Is that actually true? Is that one of yours?
It is true. What do you mean, is that actually one of mine? It is actually true.
That's great.
Yeah.
I'm going to link that for one of my lectures. I don't know how I'm going to get it in, but yeah.
That is the student t-test. William Gossett, born in Canterbury. Now, this student t-test is very limited because it only applies to continuous data samples must come from normal distributed populations. The samples must be independent of each other. Independent. And what that means, we will discuss later on, probably tomorrow. This particular case here also assumes that that the populations have the same population standard deviations and samples have the same sample size. Okay? That's a hell of a lot of stipulations. And usually, if one of them is violated, things start to go wrong. And you get, bless you, and you get some weird numbers that you really don't want. So that is the t-score. And I say something about these stipulations probably tomorrow. That is the t-score. And what we do with this t-score is we use the t-score use the test score to calculate the p-value. Or we rather use a calculator or a computer to calculate the p-value. And check then what this p-value is that the calculator gives us. Then we go back to our protocol. So we find the p-value. We find the p-value, calculate that. And we then go back to our decision rules. We've got a p-value, and we say, if p is low, H naught must go. If p is high, H naught can stay. And based on these decision rules, we then make the decision. We reject or we fail to reject the null hypothesis according to these rules. So that is basically the protocol that we are going to use. So just for fun, for whatever reason, whatever the samples are, we set our null hypothesis, no difference. We said alpha is 5%. Our decision rule, if p is low, H naught must go. We calculate the test score, and from the test score, we calculate a p-value. Let's say we've got a p-value of 0.8. We said it's a probability, can be between 0 and 1. What would be your conclusion? Loud?
You'll keep the null hypothesis.
We keep the null hypothesis. We fail to reject the null hypothesis. You are absolutely right. Fail to reject the null hypothesis. because P is larger than alpha. If P is high, H naught can die. So we made a decision. There might be a slight chance that we are wrong, that is this type 1 error, but it only happens 5% of the time that we are wrong. And we made the decision. We believe that there is no difference between the populations from which the samples were taken, and everything that we observe, any differences between the samples that we see, is just simply down to sampling error. Here's another one. H naught, no difference. It's always the same. Alpha, 5%. P-value equals 0.048. What should be our decision? Our decision should be, we need to reject the null hypothesis because the p-value is lower than our threshold. So if I give you a p-value and I give you a significance level, you can immediately say, yes, we reject the null hypothesis, or we fail to reject the null hypothesis. If we reject the null hypothesis, we say there is evidence that the samples are coming from two different populations. There is a difference. Make sense? It's simple, if you think about it. The only complicated thing, there are two complicated things. The only complicated thing is really calculate the p-value. And the other one is choosing the right test with all these weird and wonderful assumptions. For the calculation of the p-value, we have software, and I'll show you that, how you do that tomorrow. Choosing the right test, oh boy, that is sometimes a little bit weird. What test should you use? You have just seen the calculation for the student t-test, but there are, I would say, a million other tests that you could use, and you need to know actually under which conditions you need to know which test. Most people are happy with 2 or 3 tests. If they know that, that's absolutely fine. The rest, that is just for the, for the anoraks. That's for the geeks who know that, under certain conditions, you can't use that test. You better use this test. And if it is Wednesday and a full moon, then you use this test, right? That's magic. But for the rest of us, we are quite happy with 2 or 3 tests that we can use. And tomorrow I'm going to show you how we can calculate these p-values for, say, this student t-test. Are you happy with that? Any questions? Can we go now? Yes, we can. Thank you very much. Have a lovely evening. Don't do anything I wouldn't do. And I shall see you tomorrow, bright-eyed and bushy-tailed at 10 o'clock? 10 o'clock.
10 o'clock.
Yes. Where we will talk about how we calculate these things. Be good. Don't do anything I wouldn't do.
Not